So first, we'll just talk about potential difference and its two types. So we already know what potential difference is. We know what current is, but we also want to know the two types of potential difference, and that's direct and alternating. Okay. So we'll talk about alternating potential difference, direct potential difference, and then we'll also talk about mains electricity. So potential difference, we know, leads to a current. And that potential difference, like we just mentioned, can be either alternating or direct. So this is alternating. That's how you show alternating potential difference, or direct potential difference in this image here. So what actually is alternating current or alternating potential difference? So because the potential difference leads to a current, if your potential difference is alternating, your current will also essentially be alternating. So alternating potential difference directly leads to an alternating current, which is this image here. And alternating, it's quite self-explanatory. All that means is that current changes direction. So the current flows in one direction, and then it goes back on itself and flows in the other direction. And that direction of the current is constantly alternating between the positive and negative. That's why it's called alternating current. So it goes one way, then it goes the other way, and then it goes back that way. So it goes from left to right, right to left, and so on. Direct current or direct potential difference is, well, the opposite of alternating current and alternating potential difference. And it does not change direction. So it just flows in one direction only, and it never goes back on itself. So in AQA exams, there's often 2-mark question that can ask you the difference between an alternating and direct current. So if you just define each one of them, that is full 2 marks. Okay. Any questions from any of that? Simple, have you heard that before? Hi, Ananya, I just saw that you joined as well. How are you?
I'm good, thank you.
Good, okay, so we're just, did you catch all of that? Do you want me to go back?
I got that.
Perfect, okay, fine. So if there's no more questions, then we'll move on. So we'll talk about AC, or alternating current in mains electricity. So the mains electricity, or what electricity is supplied into our homes, houses, businesses, whatever else, they essentially supply alternating current, which we represent as AC. And of course, we now know that alternating current is always changing direction. DC is usually present in batteries. So the batteries or cells or your AA's or AAA's that you put in your TV remote and things like that, they supply direct current. So again, direct current just means that it's passed around the circuit in one direction only, and it doesn't change direction, or it doesn't reverse direction. So batteries or DC are shaped to only let current pass one way into the battery socket. So that's why you always have to put the battery the right way around. Otherwise, it doesn't let the current flow through. Yeah. But if the batteries conducted or had alternating current instead, then it wouldn't matter which way you put the battery in. But just remember, because you have to put the batteries one way around, a specific way around into your remote control, that is why that the reason for that is because they have direct current, so it can only flow one way, so it has to be correct. We'll talk a bit about frequency as well. So what essentially we want to know is that AC, or alternating current, supplies that come through that have alternating current, they also have a frequency, and that frequency is determined by, or defined as, the rate of direction change. So any frequency is of course the rate, but it depends on the circumstances at what rate we're talking about. So in this context, the frequency of an AC supply is the rate of direction change. So the mains that supply your AC, or alternating current, run at 50 hertz. And hertz, we've heard of hertz before. Hertz are the SI unit for frequency. Happy with that, everyone? Okay, there's no
Yeah.
questions anymore. Yeah, good. Okay, so essentially 50 hertz just means that the current changes its direction 50 times per second. So number of times per second is 50. That's why the mains alternating current runs at 50 hertz. So this is your frequency. Another value that you need to know is the voltage of your mains, and that is 230 volts. And that is country dependent usually, but when we talk about the UK, the electricity that we get through the mains, we get 230 volts of it. So sometimes they might give them to you in an exam question, sometimes they might not. So it's only going to benefit you if you could just learn that the mains runs at 50 hertz and 230 volts. You would have covered circuit diagrams in your previous webinar last week if you attended it. So most of the voltages were around 2 to 8 volts when we draw a circuit diagram. So the main supply, you can imagine, has a huge amount of potential difference, 230 volts compared to 2 to 8. That is why the electricity in homes is so dangerous, because it's carrying a very large amount of potential difference. And that's all that we wanted to know about direct and alternating potential difference. Okay. So just shout the answers out whenever either one of you. What do we think? Is mains an AC or alternating current supply or a direct current supply?
Alternating.
Yeah, exactly. And we all obviously already have covered this, so AC is just alternating. Okay. Fine. And DC? I know you guys already know this.
Direct.
Perfect. Yeah, exactly. So if you had to define them both, so we just talked about, sometimes it can come up as a 2-mark question, what would you say exactly for each one of them?
An alternating current runs like reversing, like constantly reversing direction.
Yeah.
And a direct current doesn't change direction.
Yep, correct. And can you guys give me an example of each as well?
For direct, batteries.
Yeah, correct, yeah. And alternating we've already talked about, haven't we? So your mains. Okay. So how you want to define alternating and direct current is essentially alternating current, like you rightly mentioned, is the current that continuously changes direction at a specific frequency. So we've talked about the frequency, so that's just the rate of change of that direction. So it'd be good to mention that not all alternating currents have the same frequency. So you can have 50 hertz like your mains, you might have 2 hertz, which is really slow, you might have 1,000 hertz, we just don't know. So a current that continuously changes direction at a specific frequency is AC. And DC, like you also mentioned, is one directional or unidirectional current flow. So it doesn't do what alternating current does. Okay. What is the frequency and voltage of the UK mains electricity supply?
Um, 50 hertz and 230 volts.
Perfect. Exactly right. Yeah. So just remember them the right way around. Just another way, a good way to think about it is the potential difference is a lot more than the hertz. So don't get confused between 50 volts and 230 hertz. So your potential difference is really, really large. That's why it's so dangerous. The frequency doesn't really change how dangerous a current is, but the voltage does. So that's why it's really high. And that's all that we needed to know about direct and alternating potential difference. Okay. Any questions from that? I think it was pretty straightforward stuff. Yeah. No questions? Fine. So we'll move on to mains electricity. So we've already talked about the frequency of the mains, and we've also talked about the potential difference of mains, but we actually want to know how they work, right? So how is that electricity coming through to the mains, and then how dangerous is it and why? Okay, so these will be your tutorial specification points. So we'll talk about how most electrical appliances are connected to the mains using the 3-core cable. And then we'll talk about how the live wire, which is a part of this 3-core cable, carries a different potential difference. Then there's a neutral wire that we'll talk about, and then there's an earth wire that we'll also talk about. Then we'll talk about how to identify them, and then the potential difference in them, and then why a live wire might be really dangerous if the circuit is open, and then potential dangers of any connection between the live wire and the earth wire as well. Okay. So when we talk about cables, essentially, of course, we need some cables to get electricity into our houses, right? That is how current is carried through cables. So these cables are used to connect to the main supply in our houses. And what they do is they provide a pathway for that electricity to run through. Specifically, the cables used to supply the mains are called 3-core cables because they're made of 3 wires. Yeah, and these all run into the head of a 3-pin plug, which can go into a wall socket. So if you look into your sockets or any appliances that you might use, there's 3 pins. And those essentially represent the 3 wires that this 3-core cable has. So it looks actually something like this, the inside of it. So it is a little bit messy, but if you just follow this track around, and I'll try and color them if I can, if it allows me to. Okay, so you have a blue, which is this one. You have a brown, which is this one. And you have another wire that is green and yellow. So now you can see them a little bit better. I think they've drawn it out as well. And that extra thing that you see here is the fuse. Okay, because every single socket needs a fuse, because if you don't have a fuse, it's going to be really dangerous. And we'll talk about why that happens as well. So you've got 3 wires, you've got a blue wire, you've got a brown wire, and you've got another wire that is essentially green and yellow. So the green and yellow that we just draw, what they've drawn a lot more neatly than I have, is the earth wire. Okay. Then the brown one is your live wire. And there's another one, which is your neutral wire, and that is blue. So now we'll talk about exactly what these wires do. So the green and yellow that we talked about here, this one, the longest one, essentially is called the earth wire. It doesn't normally carry a current, so the potential difference is 0. Okay, and it's only present as a safety mechanism for us to stop the appliance from becoming live. And what that means from becoming live is from carrying current. Because if you use a toaster and you didn't have an earth wire, and that live wire accidentally touched the body of the toaster, if you touch the toaster, you're going to catch that electricity. So that is why you need an earth wire as a safety mechanism to stop that appliance from becoming live. And it only carries a current if there is a fault in the circuit. Normally, it's 0. The current is 0. The potential difference is 0. But if your current messes up, or your current or your circuit is considered dangerous by the earth wire, then it will take some of that current and conduct some electricity. Okay. The live wire is the second one that we need to talk about. This one, the brown one here. Essentially, that is the wire that carries all the potential difference in the current. That is what will power your toaster, for example. And this live wire in the UK a live wire connected to the mains will have a potential difference of 230 volts that we've already talked about. And this starts off the flow of current through the circuit. So the live wire is the beginning, or essentially the wire that conducts the electricity through a circuit. And in the UK, the potential difference that a live wire carries is 230 volts. And the third and the final wire that we want to talk about is the blue one. And it has its own purpose as well. So it's blue, first of all, to identify. And this neutral wire essentially makes the electricity leave the circuit relay. So the electricity flows out through this wire. So it completes the circuit in a way that the electricity flows out of it. But it doesn't carry any potential difference. So another component that we talked about was the fuse. So 3 things that we want to know happens in what a socket looks like is a brown wire called live wire, a blue wire called the neutral wire, and then the earth wire that is covered in this yellow and green insulating material. And next to it, we also have a fuse. In exams, it's actually pretty common for them to draw that out and ask you to label it as well. So just make sure that you know what color represents what wire and where do they kind of go as well. Okay. Now, we've talked about what it looks like, but we also want to talk about why they're dangerous and how they're dangerous as well. So we said just now that live wire has an alternating potential difference of 230 volts from the main supply. And that is really, really high compared to what you guys or I do, or anyone actually, a normal human carries in their body, and that is 0 volts. So we, on a normal day, don't carry any potential difference. So from 0 to 30, 230 is a massive jump. So accidentally, if you touch the live wire, bad things are going to happen. Okay. So open circuits are dangerous. So an open circuit means that if your neutral wire is broken, let's say, the circuit is not complete, and that is going to be dangerous if you touch it. And why that's the case, it's because there is some potential difference in that circuit still. And when you touch it, that current that has nowhere to go because it's open can flow from the live wire through your body, because your body is a conductor of electricity, and then through your feet into the earth. So you will essentially complete the circuit if the circuit is open. So whenever there is a connection between the live wire and the earth, a current usually flows. So usually this connection comes in the form of a person touching the live wire. So there is a pathway from the live wire through the human body and down into the earth, because we know that human bodies are conductors of electricity. Okay. Other dangers of electricity that we want to talk about are water, fuses, sockets, and wires. Okay. So water. Can anyone think about why water is dangerous? Doesn't have to be right, just take a guess. No ideas? Okay. So water can conduct electricity, okay? And this will also provide a path for electricity to flow into your body. And that's why usually our parents tell us, or everyone tells us, oh, don't touch a socket with wet hands. And that's the reason why. Okay. So it's really, really important, actually, scientifically, to use dry hands when you're operating any appliances or touching any sockets, because that water that is going to be on your hand can conduct electricity and then to your body, and then down to the earth. So you'll be completing that circuit. Okay, so really important also in real life. Fuses then also something that we want to talk about. So when an electric circuit becomes overheated, it can lead to a fire. So if anything becomes overheated, it can lead to a fire. And that's why we have a fuse as a safety mechanism, because that fuse, what it does is that it shuts down the circuit if the current becomes too high. So it breaks the circuit. So it melts usually. So it breaks the circuit by melting if the circuit reaches a certain temperature. So if a circuit reaches a certain temperature, it means that it's overheating, and the wire will melt, break the circuit, and there will be no current potential difference passing through that circuit. And the third thing that we wanted to talk about was sockets and wires. So these sockets, if you look around, or the wires that we use, chargers, whatever else really, they have an insulating coating covering it. And that is really, really key to prevent us from having direct contact with the mains. Okay, because it's insulating, because of that insulator, it's not going to conduct electricity. That is why when your wires become a little bit old or frayed, it can expose the live wire from inside the insulating material that usually keeps us safe from the live wire. And that's why wires that can become cut or frayed can expose this live wire and become really dangerous. Okay. Any questions from anything that we've done so far? Any questions? If you guys don't have any questions, I'm going to do some questions with you. So what do you think? So how many wires are usually in cables connecting electrical appliances to the mains? And what are these called?
Is it 3?
Correct. And what are they called?
There's a live wire, there's an earth wire, and a neutral wire.
Correct. Absolutely right. Yeah. So 3 wires, live, neutral, and earth. Perfect. Okay. So what color did we say that the earth wire was going to be? So I'll give you options. There's blue, brown, and green and yellow.
Green and yellow.
Yeah, exactly. Yeah. So just remember, Earth has got is green. Well, it's blue and green, but that helps me remember. So don't confuse yourself between blue and yellow and green. Just think of grass when you think of the Earth. Okay.
Sorry, just to let you know, someone's answering in the chat as well.
Oh, sorry, I would have missed that. Hi, Mackenzie. Sorry, I'm so sorry. I didn't read the chat at all. But yeah, you're absolutely right. So live, earth, and neutral, and there's green and yellow. Perfect. Okay. Are you able to unmute yourself and talk at all? Because it might be a little bit hard for me to keep an eye on the chat if I'm sharing my screen. If not, that's okay. Oh, perfect. Okay, amazing. If you can't, then just give me a heads up and I'll keep checking the chat as well. Okay. Fine. So now we want to know the insulation color on the live wire. So you've got, yeah, exactly. So brown. The closest way to remember it is think of red, because red is bad, red is live. It's just a dampened down version of that, really. No one knows why it's brown, but it is. Okay. earth wire, it shouldn't say that. What should it say if it's blue?
The neutral wire.
Yeah, exactly. So why does the earth wire not conduct any current, and does it at any point, and why does it if it does?
It's only if there's it only conducts it to the ground as a safety precaution.
Yeah, exactly.
Because it transfers all the voltage to the ground if the voltage becomes out of control or something. Yeah,
correct. So that's a really good answer. So under normal conditions, no current flows through the earth wire, so zero potential difference, zero current. But if there's a fault in your circuit or your appliance, let's say there's a surge or the casing becomes live, so anything bad happens really, that current will pass through the earth wire and into the ground, so nothing bad happens at home. Okay. What potential difference does the neutral wire carry?
0 volts.
Yeah, exactly. Yeah. And state the potential difference between the live and the earth wires. Go on.
Pretty sure live is to complete the circuit and earth is just as a safety precaution.
Mm-hmm. So what potential difference do you think flows between the two?
Oh, I've forgotten the voltage. Is it 230?
Yeah, correct.
Okay.
Yeah, it is 230. So it's a weirdly worded question actually, because state the potential difference between the live and the earth wires. It's asking for the difference, but then potential difference on its own is also a phrase that we use. So essentially, if the earth wire conducts 0, the live wire has 230, the difference is going to be 230. Or if you think about it, if the earth wire comes into play, if there is a use of the earth wire because your appliance has got something's happened to your appliance or your circuit is not how it should be, then that 230 volts of potential difference will be distributed between the live and the earth wires. And why do we have the neutral wire then?
Electricity flows out through it.
Exactly. Yeah, exactly. So what it does, it completes the circuit by connecting the appliance back to the main supply. So it goes back, you're right in saying that, but what it does when it takes that current away is that it completes the circuit. So if you don't have a neutral wire, your circuit is not going to work. For metal appliances, so let's think of, let's say your toasters, your fridges, your TVs, hair straighteners, things like that. Where do you think the earth wire is connected to?
Is it like the top with the plug, like the top pin?
Yeah, it is. That is, you're right in saying that. But what I think they're trying to ask is that it is connected to the metal of the appliance. Can anyone think of why? Why the earth wire would be connected to the metal? Why do we want a wire connected to the outside, essentially, of the appliance? Any wild guesses at all? No? That's okay. So that is essentially the last question that we wanted to cover. So why is the earth wire actually connected to the casing in metal appliances? It's because, let's say the live wire becomes too loose and touches the casing, the current will flow through that metal appliance if you don't have the earth wire. But if you connect the earth wire to the outside of your appliance, essentially, or the metal casing of the appliance, then the earth wire will take the current instead. Okay. If you didn't have an earth wire and you touched that casing that had a live wire touching it, then you'll be electrocuted. But that doesn't happen because there's an earth wire that is actually attached to the casing that takes that current then, if the live wire becomes loose.
Um, I'm not sure, like, is there an example of this? Because are we talking about like the casing of a plug or the casing of like an actual appliance, like a kettle or something?
Both. So let me find a photo. So this is the best photo that I could find. Let me see if I can. Do you think I can add a photo in the chat? Does that work? I've never done it before, but no, it's just giving. Okay, fine. Ignore that. I will stop sharing my screen and I'll share it again in a second. So I'll show you a photo that would hopefully make more sense. Okay. Can everyone see that? Yeah. If I make it a little bit bigger. Okay. So these are your three wires. You've got your live, neutral, and earth. And the earth is actually connected to the outside of a cooker, let's say. Okay. Another example, washing machine. So because the washing machine is usually metal or, well, plastic and then metal inside, that earth wire inside, because I know you guys are thinking of just the sockets, but the sockets come from the appliance, right? So where that wire actually originates from the appliance, that is where the three split up. So the three split up in the washing machine, and then there's a wire, and then they split up again into your socket. So we're talking about inside the appliance, how are they connected? Does that make sense a little bit? So something like this. So you have your wire that you have plugged into the mains, and that earth wire goes into its socket, but it's connected to the casing, the outside of it as well. So just in case this live wire touches the casing in some odd occasion, something happens, it comes loose here, touches the casing, this earth wire can take all the current and prevent electrocution. Does that make sense a little bit?
Yes, thank you.
Okay, that's fine. So what we'll do now is that we'll try some exam questions. Say, let me just make sure that it's titled. Any questions from anything that we've done? Or any other questions at all?
I have a question from a completely different topic that I was wondering if you could help with. It's from momentum.
Okay. Shall we stay a little bit later on and then we'll talk about that as well? Yeah?
Yes, thank you.
So let's do this one first. So I'm going to share my screen again. Everyone can see that now? Yeah? Okay. So what do we think? of the first question. Any ideas? It's a circuit with a battery. What do we say about battery?
It has like a direct current, which means
Yeah.
it goes in one direction.
Yeah. So you saying that the current is always in the same direction. So C. Yeah, correct. Okay. Now it's asking you to calculate the potential difference across the battery in the circuit here. So you've got the current, you have the resistance, you want to calculate the potential difference. How are you going to do that? They've also given you, they've been really nice, and they've given you the equation as well. So potential difference is current times resistance. What do we think? How are we going to calculate it? No answers? So, yeah, go on. Yeah.
Which is 0.4 times 30, which is 12.
Yeah, exactly. So your resistance, you have two resistors that are connected in series. So your total resistance is going to be R1 plus R2. So your total resistance is 30 ohms. And then they've already given you the equation, which is your potential difference is your current times your resistance. So V is IR essentially, and your V here is going to be B is going to be, I don't know what's going on. B is going to be 0.4, like you mentioned, times 30, which is 12. What are the units? What should I write?
Volts.
Yeah, exactly. Okay. Happy with that? Yeah. So your potential difference is just going to be 12 volts. Okay. And then it says the equation which links current, potential difference, and power is power equals current times potential difference. So can you please calculate the power output of the battery and give your answer to one significant figure? What do we think? So they've said P is I times V. You know V, you've just calculated it here. You know I, they've given it to you in the question. So it's going to be 0.4 times 12. And that's going to be 4.8. Just remember it's one significant figure, so you're going to round that to 5. They've given you the units already, and the units for power are watts. So 5 watts. Okay. Is that what you guys were thinking as well?
Yeah.
Okay, good.
Yeah.
Amazing. Okay, so now they've said there's an electrician that's replacing an old electric shower with a new one. And they've shown you the inside of the old shower here. And they've said he shouldn't change the shower unless he switches off the mains electricity supply. Explain why. 2 marks.
Water conducts electricity.
Yes, really good. Yeah. So what's that going to do?
He might get electrocuted because if he touches the live wire.
Perfect. Exactly right. Okay. So he just might get electrocuted or might get an electric shock if he touches the live wire because water conducts electricity. Yeah. And that is your answer. Perfect. So they've said then that the new shower has a power output of 10,690 watts when it's connected to the 230 volts mains electricity supply. And they've given you the equation again. Can you please calculate the current that passes through the new shower and give it to 2 significant figures? And that is a 4-mark question. So I'll go back here so you have all the values that you need.
I don't have a calculator on me, but do you divide 10,690 by 230?
Yes, perfect. And you get around 46.478, something like that. And 2 significant figures would just be rounded down to 46. Okay. And is everyone okay with that? Or shall we I'll just write it out anyway. So you have your equation that they've given you here. So I is P over V. You want to find the I, so they've rearranged it for you as well. So all you have to do is put in your numbers and put that into a calculator, and then you get your answer. Just remember how many significant figures, because that's what's going to catch people out the most. Okay. Then it says that the new shower has a higher power rating than the old shower. How does the power of the new shower affect the cost of using the shower? And give a reason for your answer, so 2 marks.
It's going to be more expensive.
Okay. Why? Why do you think?
Because like more energy would be used per second.
Perfect. Exactly right. So just remember the equation for power. So power is energy over time. Yeah, rate of change of energy is power. So if it has a higher power rating, it's essentially using more energy over the same given time. So it's going to be more expensive. So those are your 2 marks. So more expensive is 1, so it's going to cost more. Why it's going to cost more is because it's using a higher energy over the same time. Okay, well done. Okay. Another question. So this is a 6 marker. Okay. Shall we do this one? It's more of a practical, or do you guys want to move on to a different question, something like this? It's totally up to you. Why don't we actually do the practical question, because it might be helpful. Okay. If you guys haven't done it before, that's okay. I'll just talk you through the answer. No takers? That's fine. Go on.
Would you use the potential difference equals current times resistance calculation?
Yeah, correct. Okay, so it says a resistor is a component that is used in an electrical circuit. How can a student then use the circuit to take the readings necessary to determine the resistance of the resistor R? So the best thing you can do in these types of questions where there's loads of marks is just do step by step. Okay, so they're saying the first thing you want to do is switch the circuit on. Yeah, so it's open here, so you're going to close it first. Then you want to read the ammeter and the voltmeter. Then you are going to, this is a variable resistor, yeah? Then you're going to adjust the VR, the variable resistor, to change the current. What that will do then is change the current in the circuit. So you will get different readings in the ammeter and voltmeter again. So read the ammeter and voltmeter. Then once you have all the readings after changing this VR multiple times, is always a graph. So you're going to draw a graph of V versus Y. Okay. And then the gradient of that, because we know that R, or your resistance, is V over I, because V equals IR. So the gradient of that graph will give you the resistance that you were looking for. Happy with that? Yeah. So 6 marks. So thinking was along the right lines. It's just that for 6 marks, you want to write exactly how you would do it, so step by step. So you want to switch on the circuit first, of course, otherwise it's not going to conduct any electricity. Then you want to read your initial ammeter and voltmeter readings. Then you want to change the variable resistor to give different resistance in the circuit. And then you want to keep taking your ammeter and voltmeter readings after you've been changing your variable resistor resistance. And then you want to draw a graph of V versus I. So V usually on the y-axis, I on the x-axis, and then the gradient will give you the resistance. So they said then, can you tell us why the student should open the switch after each reading? And that is 2 marks. Why is that important? What happens if you use a hairdryer for too long, let's say? Gets hot. Sometimes it gets too hot that it just turns off itself. Yeah, which is why, same concept here, is that you want to open the switch. What that means is that you want to turn the switch off, because opening is switching it off and closing the switch is turning it on. So the resistance doesn't increase, because if you didn't switch it off, then the resistor would get hot, and the resistance of that resistor will increase. Okay, does that make sense a little bit?
Yeah.
Okay, perfect. And then we'll do this calculation as well. So in an experiment using the circuit, an ammeter reading was 0.75 amperes. The calculated value of the resistor of resistor R was 16 ohms. So what is the voltmeter reading? You know what, I'm not even going to make you do this calculation, because I think you've probably done it multiple times. So it's just going to be V equals IR. So that is going to be 0.75 times 16. And that is going to be 12 volts. Okay. So this is your golden equation in electricity. So just remember which way around it goes, and it's going to help you in most of the questions. Okay. Then it says that the student told his teacher that the resistance of R was 16 ohms, And the teacher explained that the resistors used could only have one of the following values, so 10, 12, 15, 18, or 22. Suggest which of these resistors the student had used in this experiment and give a reason for your answer. So the teacher's saying, okay, 16, fair enough, makes a little bit of sense, but we actually only have 10, 12, 15, 18, and 22 resistors. So 16 can't be the actual value. So which resistor do you think that they used and why? If you had to guess, which one would you go for?
15?
Yeah, exactly. So you'd go for 15 because the closest to 16, isn't it? So that would actually have gotten you marks if you just said, well, it can be 15 ohms instead of 16 because the closest to 16. But if you want to understand why, then think about why we were switching it off. So we were switching off to prevent the resistor getting too hot. But it's not an ideal world, is it? So even if you switch it off between readings, the resistor is still going to get a little bit hot and increase its resistance to what it should be. That could be one of the reasons. The second reason could be that he might have just plotted it wrong a little bit. One reading might have been off to give him 16 instead of 15. Any of them. You don't even have to write that. All you have to say is that 16 is the closest to 15, and that's it. That would have gotten you marks. Okay. And we'll do this last question. So it says that the diagram shows a fuse. It says 5 amperes, and describe the action of the fuse in a circuit. So how does a fuse work?
If the current is above 5 amperes, then it will just like melt.
Yeah. And then what will it do? Last mark.
It will like stop the flow of the electrons, not the electrons, the current.
Yeah, exactly. So whatever value is written on the fuse is the maximum current it can carry. So if it carries any more than what's written on the fuse, so 5 amperes in this situation, if the current increases to more than 5, what it's going to do is that it's going to melt, okay? Because it's going to think that it's overheating. And when it melts, it's going to break the circuit. That's all you need to say for 3 marks. So when the current increases to over 5, the fuse is going to melt and it's going to break the circuit. That's it. Okay, happy with that? Any questions whatsoever? No questions? Fine, so let's do this last one. So it says that the picture shows 6 different household appliances. Some of them we already talked about. And 4 of the appliances, including the fan heater, are designed to transform electrical energy into heat. Can you name the 3 other appliances that transform electrical energy into heat?
The iron hairdryer and kettle.
Exactly. Okay. So why does a table lamp get hot then if you're using it?
The table lamp gets hot because heat is a waste product.
Exactly. So just remember when it's asking you to include appliances that are designed to produce heat, they're not asking you for appliances that release heat anyway, but it's a waste output. Okay, so table lamp is an interesting one because it actually does get hot if you sit under a table lamp, or if you're working with a table lamp, it will get hot there, but that's not what it's designed for. It's designed for light. Okay. Any questions from anything that we've done today? We've covered a fair bit, so any questions whatsoever? And we'll do your question on momentum as well now. Okay. But if other people don't have any questions, you feel free to go. That was it. That was all that we needed to cover.
Thank you.
No problem.
Thank you for the lesson.
No problem at all. Can you can still hear me, right? Yeah.
Yeah, I can.
Yeah, perfect. Okay, go on.
Should I just read out the question because it's quite long, I think.
Let me see if I can actually give you host access, but I really doubt. Can you maybe copy and paste it in the chat? No.
I can just type it up. I'll just do that quickly.
Yeah. Or if you can read it out as well, that's fine. I'll try to get the most of it.
Oh, yeah, I'll do that.
Yeah.
So it's from the chapter 5 forces, and it's about momentum.
Yeah.
In any collision, the total momentum before the collision is equal to the total momentum after the collision. Oh wait, this is just the formula. It's just the m1 u1 plus m2 u2 equals the m1 plus m2 in brackets with the v outside of the brackets.
Yeah.
And this is the actual question. A shopping trolley of mass 2 kilograms travels at 8 meters per second towards a stationary trolley of mass 2 kilograms.
Let me draw it. So I'm going to share my screen. I'm going to bring out a blank page and you tell me if what I'm writing is correct. Okay.
Okay.
So let me just share my screen. Okay. So you're saying there's a trolley. Let's draw our trolley. That is 2 kilograms.
Yeah, and it's traveling at 8 meters per second.
Okay.
Towards a stationary trolley of also mass 2 kilograms.
Yep. So 0 meters per second.
Yeah. After colliding, the trolleys move together. At what speed do they move?
So then what happens is that 2 kg, 2 kg. So we don't know V. Yeah. So what's the equation that they said that you're going to use?
Well, just above the question, they put the law of the conservation of momentum.
So m1u1 plus m2u2 equals, go
on. In brackets, m1 plus m2, and then close brackets, and then v.
Yeah. Okay. So what we don't have is this v here, isn't it? That's what we're trying to find. Yeah. So how we're going to go about this is we know m1, which is 2 kg. We know u1, that is 8. So let's just assume that they are traveling they're traveling this way, and that's positive. Okay. And then we also know the value of the second mass, which is also 2. Let's put it in brackets so it's clearer. But it's stationary, so its u is 0. Yeah. And then you know m1 and m2 again, so it's going to be 2 plus 2. And then you have your v again. Okay. So when you do this calculation, you just get 16 plus 0, because 2 times 0 is 0, and then 2 plus 2 is 4 times v, and then v is equal to 16 over 4, and that is 4 meters per second.
Yeah, that was the answer I got, but my physics teacher marked it as 8.4 meters per second. I think she might be wrong, so.
Yeah, I think there is no way to get the answer, I'm afraid. So I think maybe just check with her. Might be an error on her part. But
yeah, I mean, the reason I'm doing this course is because she's not a particularly great teacher anyway.
Oh, okay. Yeah, so just question and maybe just be like, what equation do I use? Because if I use this equation, then I just get 4 meters per second. Yeah, and that it's a fairly straightforward question if you think about it. So they've given you the equation as well. So if you just put down all the numbers, that is the answer that you're going to get. There is no doing it wrong. Do you know what I mean? So 8.4 is definitely wrong unless I'm doing something wrong with the fundamentals, but I think you're right. Okay, I think it's 4 meters per second.
Yeah, thank you for the help.
No problem at all. I will see you next week maybe.
Thank you. Bye.
No problem. Bye.